Okay, so this is now lecture 11, part 2. Now I'm going to start talking about new stuff. How do we specify a position of something in regular space? Okay, so in regular space, a position is given by a position vector r, x, y, z. In spacetime, a point in spacetime, remember spacetime is really a space of events. It's a set of events. An event is given by a position. It's called a 4 vector. And you might say, what's up with the 4? Well, first of all, it has 4 components: CT, and then X, Y, and Z. So that's where the 4 comes in. Now, it is not a vector in the strict sense of the word. So what I'm going to do in this lecture is I'm going to say some things that are basic and some things that are optional and advanced, slightly more advanced. If you are overwhelmed with this class, you can skip over them. I'm going to use a different color ink. Okay, so I'm about to say that, but for now, I'm just going to say the minimal thing you need to know. A 4 vector is a quantity that transforms under Lorentz transformation. Okay, so 4 vector is any quantity that transforms under Lorentz transformation. Space and time is an example. So we have CT prime equals gamma CT minus V over C X. We have X prime equals gamma minus V over C CT plus X. We have Y prime equals Y and Z prime equals Z. So here's an example, okay? Any set of 4 numbers that transform from one reference frame to another, and according to these, is called a 4 vector. That's kind of a definition of a 4 vector. Let me just pause for a second and check that I didn't make any mistakes. Oh, no, I'm going to resume the share. It's just a second. But it doesn't have to be just the position. Let's say if I have a vector, any vector, a 4 vector equals a naught, a1, a2, a3, we will see an example, energy and momentum actually form a 4 vector. Another example of 4 vectors is electric field and magnetic field. So things like that. So as long as you go from A prime to A by this rule, that's a 4 vector. So in this case, it would be A naught prime equals gamma, A naught minus V over C A1, A1 prime equals gamma minus V over C A naught plus A1, A2 prime equals A2, and A3 prime equals A3. Not position, not X, not time, but just some set of 4 quantities that transform from one frame to another. And according to this rule, boom, it's a 4 vector. Now, I'm going to say something that's slightly more advanced, and you can skip over that if you wish. There is, again, an analogy with rotations that might help you. If I ask you, what is a vector? You might say something like, it's a thing, it's a set of numbers, or it's a mathematical quantity that encodes both position and direction. A vector is something that has both position and direction. When you take linear algebra, you learn that a vector is something that lives in a linear vector space. Another definition of a vector is it's any set of numbers that transform in a specific way under a rotation, not switching between co-moving frames, but a different type of a transformation called rotation. So what is that specific transformation that those numbers have to obey in order to be considered a vector? So for rotations, so, let me just say this. And the transformation is x equals x prime cosine of theta. And the theta is the angle by which a coordinate system is rotated, minus y prime sine of theta. Y equals x prime sine of theta plus y prime cosine of theta, and z equals z prime. This is a special case of a rotation around the z-axis, but you can generalize to an arbitrary rotation around an arbitrary axis. Okay, if you have a vector that's pointing there, and you rotate your coordinate system, and in the new coordinate system, that vector takes a different set of components. Of course, the values of components will be different. But if the components in one frame and another are related specifically like this, in this case for rotation around the z-axis, but there's a generalization, then you're dealing with a vector. An analogy to that, I give you 4 numbers, and they transform from one frame to another specifically in accordance with the Lorentz transformation, then it's a 4 vector. Okay, so again, there is a rotational analogy. Now I'm going to go back to a regular presentation. So any 4 vector will have an invariant. So I gave an example with the vector 4, just 4 vector with 4 quantities that happens to transform from one reference frame to another by Lorentz transformation. Then it's automatically a 4 vector. Well, it automatically has an invariant, and the invariant would be minus a0 squared plus a1 squared plus a2 squared plus a3 squared as invariant. An example, we already saw an example with position, right? So ct squared plus x squared plus y squared plus z squared. And there's an equivalent for the deltas, for the intervals. Any interval can be formed into, again, just x, y, z, and t if you place the first event at the origin. So I sometimes switch back and forth between having deltas and not having deltas. Okay, so what about it? What was the point of this quick math lesson? We defined position and spacetime, the 4 vector position. In regular mechanics, what is it that we do after we talk about position? Well, the next thing is we talk about a velocity. Okay, so far what we did in this class, we only talked about spacetime, the stage on which all physics takes place. And we want to talk a little bit about mechanics, how things evolve, how things move, interact on that stage. in a way that's constrained by relativity. Relativity places a constraint on what can happen on top of that stage. It's a different stage, so it has different rules. When we talk about velocity, right, in non-relativistic mechanics, a parameter of motion is time, which is considered absolute. Motion is described by evolution of a position vector as that parameter time evolves, right? So in regular mechanics, so motion, let me talk about motion. So in regular mechanics, we have a situation like this. We have x, y, and a particle is moving, and you have a motion diagram with a parameter. This is t1, t2, t3. And at each value of the parameter, you can assign a position vector. And then, once you've realized that time is a parameter that parameterizes your trajectory, and a position vector is a quantity that describes the position, you can start talking about how the position vector evolves with that parameter, right? So you can talk about r at t1, r at t2. You can define displacement vector. And then velocity is defined as the rate of change of position with respect to that parameter. Velocity equals the limit as delta t goes to 0 of delta r divided by delta t. Okay, and we can see from this definition, as delta t goes to 0, the velocity vector becomes tangential to the trajectory, and the faster the position is changing at a given instant, the longer is the velocity vector, right? So we have a velocity vector. I'm going to use a green color. This is an instantaneous velocity vector. We have instantaneous velocity vector, and so on. But to do this, we had to decide on a good parameter that parameterizes the trajectory. Okay, so in regular mechanics, time is a parameter that parameterizes motion, parameterizes a trajectory. And if we think about now, is the question is how to extend this to space-time. Is time still a good parameter? Well, time presents a difficulty because time is different in different frames. We want a simple parameter that's uniform, universal for all frames. So what is a good parameter along a trajectory in space-time? And the answer is it's the proper time, right? Proper time is an invariant. While the amount of time between ticks on a clock attached to a particle is measured to be different in different frames, observers in all frames will agree how much time has ticked off on the particle's clocks. So for example, if a particle is a bird, as the clock attached to the bird ticks 1 second, the time between the same pair of events, say one flap of bird's wings, measured on my clock as I sit on the ground would be 1.1 second. And the time measured by someone on a train between the same two events would be 1.3 seconds. Okay, I'm of course exaggerating. Bird doesn't fly that fast, but the time is different. But we would all agree that the clocks attached to the bird, sort of bird's personal time, that's why it's called proper time, we would all agree that that clock ticks off 1 second. So proper time is an invariant, and it is a good parameter to parameterize trajectories in space-time. Okay, so in space-time, if you have you have CT axis, and you have a trajectory. So you have the reading on the clocks attached to a particle is the parameter. That's a good parameter, and it's going to make things simple and very similar to regular mechanics. So this is tau 1, tau 2, tau 3, tau 4, and so on. So proper time, so when you say proper time, ooh, this is interesting. Okay, let me circle this, and this. Okay, so proper time is an invariant, and therefore it's a good convenient parameter. Okay, thus we can define a four velocity, or as dr or d tau, okay, which is the time derivative of ct x y z. So here I only drew the one-dimensional analog, but you can extend this to higher dimensions. So for example, so this is x, this is y, and this is ct. And let's say I'm going to use a different color so you can see, let's say there's some kind of a particle evolving on a trajectory, and this is tau 1 equals, this is tau 1 equals 0, this is tau 2, then it's moving faster with respect to proper time parameter, and slower than faster, and tau 4, tau 5, and this four velocity vector in space-time is also tangent to a particle's world line. Remember, we discussed trajectory in space-time is called a world line, and so its four velocity is tangent. Here it's smaller, here it's larger. It's tangent to the world line. So this is 4, something like that. Okay. Now, when analyzed in a particular frame, we know how to relate time span in that frame or time in that frame to the proper time. Time dilation. So therefore d tau becomes gamma d dt. And so the four velocity becomes gamma c, gamma ux, gamma uy, and gamma uz. Okay? And gamma is again 1 minus 1 minus u squared over c squared, taking square root. So I'm in some frame, I'm observing some particle motion. The particle's proper time is tau. The derivative of its position vector in space-time is the four velocity. And in my particular frame, the four velocity will have these components in a particular frame. So ux, uy, and uz are components of the particle's ordinary velocity in that frame, right? So ux, okay, a regular velocity. Okay, so these are kind of definitions. Let me pause. Now, a four velocity is a four vector. is a 4-vector. And you can see that because the 4 velocity is dr for d tau, which is d c t dx dy and dz divided by d tau. Okay, and d tau is a scalar. D tau is an invariant. It remains invariant from frame to frame. So only the numerator changes from frame to frame. And we already discussed that intervals, including infinitesimal intervals, are 4 vectors. So therefore, this is just a 4-vector divided by a scalar, which is also a 4-vector. Okay, 4-vector divided by d tau, which is a scalar, just a number that doesn't depend from frame to frame. It's also a 4. Then such a hybrid quantity is also 4-vector. So notice it is a hybrid quantity. The space-time displacement, what's in the numerator right here, is measured in some particular frame. T, X, Y, and Z, they're frame dependent. While time, the proper time, tau, is measured specifically in a frame of a particle. It's a hybrid quantity, but this is exactly what makes it transform like a 4-vector. If I insisted on having dt in the bottom instead of d tau, then the ratios would be cumbersome. Then both the numerator and denominator will have to transform from frame to frame, and it would not be a 4-vector. On the other hand, the 4 velocity defined is a very natural extension of what we think of as velocity. Okay, and it is also a tangent vector to a particle's world line, because what's upstairs is a displacement 4-vector, and you divide that displacement 4-vector by an interval of the parameter along the world line, so you get an average for velocity, and you take the time interval, the proper time interval, smaller and smaller, it becomes an instantaneous for velocity that will be tangential to the trajectory. So it's a very natural extension to the space-time. Now, the 3 spatial components of the 4 velocity, as we discussed before, right here, is gamma times the ordinary velocity of a particle measured in some particular frame. And this is slightly more advanced, but it is a projection of the 4 velocity on the spatial part of the space-time. So it's a projection of the 4 velocity on the particle slice of constant time. So you can think of something like this. This is x, this is y, this is ct. So here's a particle's world line, and at this point, it has a 4 velocity that's tangent to the world line, and this 4 velocity has a projection right here onto this plane, right? And so this projection is given by gamma times the regular velocity. Okay, and then there is also the time component, the component of the 4 velocity along the CT axis. So we will investigate that in a bit. Okay, so now I'm gonna again open a box and say something that's slightly more advanced information that you can skip if you wish. So I'm gonna use a different color right here. So note, so advanced information, so that note the quantity minus c dt squared plus dx squared plus dy squared plus dz squared divided by d tau squared is an invariant. Upstairs is an invariant because it's a space-time interval. And the downstairs is an invariant because we already discussed that Proper time is an invariant. So if it's an invariant, it takes the same value in any frame, including in the particle's own frame. So if it's an invariant, it's easiest to calculate it in the particle's own frame. Okay. So calculate. Well, in the particle's own frame, dx, dy, and dz equals 0. And dt equals d tau. Okay. So this invariant has a value of minus c squared. So therefore, the magnitude of the for velocity, it's just the magnitude of the for velocity, right? So this is just the magnitude of the for velocity. Takes on the value of minus c squared. This is very interesting. We interpret that as the square of the force speed is the same from all frames. Okay, it says that everybody's speed in space-time is the same, regardless of what frame you look at it. A particle in its own frame moves only through time, so its for velocity vector is pointing strictly in the temporal direction. The same particle's for velocity vector viewed from a different frame is tilted in that other frame, and it has a spatial component and the temporal component. But it has the same speed, so everyone moves through space-time with the same speed. And that speed is independent of the reference frame. And it's the force speed that I'm talking about. Of course, not the spatial speed, but the magnitude of the for velocity vector. Okay, you could call it this, the force speed. It's the same for everyone. We all move through space-time with the same speed, with a little asterisk, okay, a little caveat. A massless particle's for velocity is undefined because its proper time is 0, as you saw in the homework problem. And its space-time interval is also 0. Okay, light like a particle has a 0 space-time interval, so 0 numerator and 0 d tau, 0 denominator. But for a massive particle, we all move through space-time with the same force speed. That's independent of the frame. Okay, now I'm gonna go back to the regular material. Yes. Next bullet point on this agenda of extending regular mechanics to space-time mechanics is to define a for momentum. Okay, and the for momentum is defined as mass times the for velocity. Now this mass is a mass of a particle measured in its own frame. So this is a definition, right? And in the definition, you're free to choose what you mean by each letter. So this is a mass of a particle measured in its own frame. So in its own frame, it's not moving. Okay, so for this reason, it's also called a rest mass, or sometimes it's called proper mass. And you might be nervous about having to memorize all these facts for the video quiz. I understand. Don't be nervous. Okay, when I ask questions in the video quiz, they're the questions about things sort of the big things, the most important things that I want you to know. This is a detail, okay? So what do I mean by, since I brought it up, I have to be precise. So what do I mean by rest mass? So if you want to measure mass of some particle in your frame, okay, so you have some particle. So first you bring it to rest in your frame, so it's sitting at rest. Now, how do you measure mass of something? You apply a force and you measure its response, i.e. acceleration. Okay, you divide the magnitude of the force by the magnitude of the response, the acceleration, and that's the mass. Okay, so rest mass is a measure of the inertia when the force is applied to a particle that's initially at rest. Nothing fancy. And speaking of forces, a rate of change of form momentum is defined to be a force, just like in regular mechanics. But we won't really need this quantity too much. Of course, the derivative is taken with respect to the proper time. So you can see if if the force velocity is a 4 vector, then force momentum is a 4 vector, and then the force is a 4 vector because you're dividing that 4 vector by a scalar, it's still a 4 vector. So defined this way, the total force momentum of a system of particles, let's say you have some kind of a reaction, particles come in, some other particles come out, but as long as it's an isolated system, the total force momentum, the total force momentum of a system is conserved when the whole system is isolated. And isolated means that there can be 4 forces that are internal to the system as particles interact, but no interactions with the outside world. Again, equivalent to regular mechanics. Let's say, yeah, so 4. And so in a given reference frame, the force momentum takes on the following form. Okay, the m comes from multiplying by m, and the rest comes from our definition of force velocity. If you look above, so if you plug everything in, then the force momentum have these forms. Okay, so now we need to understand what the temporal and the spatial part of the force momentum mean. They have a meaning. The spatial part is called a relativistic momentum. So this is temporal part, temporal part. It's like the CT, it's like the first term in the 4 vector, like the time. So remember, if we have a position 4 vector, CT, X, Y, Z. So this first term sits in the first slot where the time sits in a position 4 vector. That's why I call it temporal. And also, this is inherited. This term right here is inherited from the CT in the very beginning. We start with the position vector, then we took the derivative, then we multiplied by m. So this is inherited from CT, and this is inherited from the XYZ. So that's why I call these the temporal part and the spatial part. So the spatial part is, I'm just going to use letter P, equals gamma times mu, which is gamma times ordinary momentum. So even though I use letter P, it's not ordinary momentum. It's this part is the ordinary momentum. And explicitly, this is the ordinary momentum divided by this square root business. Okay. So we will discuss that. And the temporal part, gamma MC. Okay. We can write it as gamma MC squared over C. The gamma MC squared is defined to be a particle's total energy. Okay. I will have a lot more to say on that, but I wanted to stop here. So we started the lecture from the definition of position, then velocity, then momentum, and it brought us to the point where we need to start digesting what these things mean. And I just basically defined it to be, the spatial part of the form momentum is the relativistic momentum. So this is called the relativistic momentum. And the temporal part, for some reason that might seem strange, I said I'm going to call it the relativistic energy, or energy of total energy of the particle. And now we will try to understand why. We will examine properties of these things, and then we will see what they mean. And we will discuss something called rest energy and what it means physically.